Welcome to another deep dive. Today we're going to be looking at modal logic.
Okay.
I think this is going to be pretty interesting, especially from a philosophical perspective.
Yeah, definitely.
Because, when we're talking about modal logic, we're talking about, necessity, possibility,
Right.
all those modalities.
Different flavors.
Yeah, and really it's all about formalizing those ideas.
Right.
Of reasoning about what must be true, what could be true, what can't be true.
Exactly.
So I think for for our listeners who are already pretty familiar with these kinds of concepts from philosophy, this should be pretty interesting.
Yeah, absolutely.
We'll be focusing in particular on alethic modalities.
Yes.
So necessity and possibility.
Right.
And I think a good place to start would be how does this differ from, standard truth functional logic?
Right. So modal logic really goes beyond standard truth functional logic, where the truth of a complex statement is just a function of the truth of its parts.
Yeah.
In modal logic, it's not so simple.
Right.
So, for example, it is possible it will rain tomorrow.
Right.
Can be true, even if it will rain tomorrow is false.
Right.
So that's like a classic example of how.
So we're introducing modal logic.
Yeah, a whole other level of analysis there.
Yeah, and what's really interesting too is even quantifiers can be seen through this modal lens as well.
Right.
Arthur Pryor pointed out that the modal system S5, which we'll get into, has a really fascinating connection to a fragment of first-order logic.
Oh, interesting.
Yeah.
Okay, so we're going to be tracing this story, this sort of historical development of, how do we get to these, these formal systems from, these kind of intuitive ideas that philosophers have been grappling with for centuries. Really.
And I think, the period we're going to be focusing on is from the early 1900s, sort of starting with C.I. Lewis. Up through Kripke in the 60s.
Right. It's really incredible.
Yes.
Like this short, intense 50-year period, there was so much development in modal logic.
Yeah, a really kind of concentrated burst of innovation there.
Yeah.
So where do we begin?
Well, to really understand, the trajectory of modern modal logic, I think a crucial starting point is the work of C.I. Lewis.
Okay.
And his kind of anxieties about the standard understanding of implication in Principia Mathematica.
Yeah.
Going back to Whitehead and Russell.
Around 1912.
Around 1912, yeah. So he was really bothered by certain theorems.
Yeah.
That, just struck him as deeply counterintuitive, right?
Philosophically.
From a philosophical perspective, yeah.
Yeah, like a false proposition implies anything, and a true proposition is implied by anything. We can represent that symbolically as neg, p right haro q, and then the other one, p right rho.
That's right.
But Lewis's point wasn't necessarily that these were wrong, within the system. It was that they just seemed to violate this, common sense notion of what it means for one thing to logically imply another.
Right, yeah.
So for Lewis, implication should be about this genuine connection, like a true logical deduction,
right.
Where the conclusion really follows from the premise.
Exactly.
Right. And so that second one that we talked about, P right or right or right arrow, it's just just because something happens to be true doesn't mean that it's a consequence of anything you can dream up.
Yeah, exactly. Yeah.
And so his worry was that, if we say that arrow, that material implication, is really what we mean by implication, then maybe propositional logic as it stood at the time was kind of on shaky ground.
Yeah. Yeah, absolutely.
And his worries weren't limited to just implication.
Right.
He also had problems with the standard way of understanding disjunction,
yeah.
Whereas equivalent to neg brit arrow q.
Right.
And he argued that failed to capture this kind of more fundamental intended meaning.
Yeah, this more intentional sense of or.
Yeah, this feeling that a true disjunction carries this weight that if one isn't the case, then the other one would have to be.
Yeah, exactly, yeah.
So it's interesting to learn that, these kinds of distinctions, they weren't completely new.
Right.
Apparently there's this guy, Hugh McCall, going all the way back to the 1880s.
Yeah.
Who was already kind of thinking along these lines.
Yeah, he was already, really distinguishing between this extensional understanding of or, and this more intentional form of implication.
Yeah.
And he argued that, primo Q shouldn't be interchangeable.
Right.
And, even if P is false or Q is true,
yeah,
that doesn't mean that, that P without Q is logically impossible.
Right.
Which is how he understood this intentional implication.
Okay.
And he even went so far as to develop this whole system where he classified propositions into 3 categories.
Yeah, certainties and possibilities and variables, right?
That's right. Yeah. So he would use these indices.
So like alpha for epsilon.
Alpha, theta, yeah. So those Greek letters with the little
superscripts.
Yeah. To kind of mark out what kind of proposition it was.
Okay.
And then on top of that, he distinguished between what he called causal implication and general implication.
Okay. So this is where beta is always true when alpha is, but beta isn't necessarily a certainty.
Exactly.
Yeah.
Okay. Whereas general implication means that it's impossible for alpha to be true and beta to be false.
Right.
So he's really already dealing with these core concepts that we now associate with modal logic.
Yeah, he's really like ahead of his time there.
Yeah, absolutely.
Grappling with these issues.
And his use of these iterated indices too.
Oh yeah.
Is pretty fascinating.
So this is like eta iota ver epsilon.
Yeah.
Meaning it is certain that it is false, that A is impossible.
Exactly. Yep.
So he's got this like really sophisticated.
Yeah, these nested modal concepts.
Yeah.
It's really remarkable.
It is kind of funny though that like Bertrand Russell initially like misunderstood McCall.
Yeah.
It seems like he didn't quite grasp that a proposition could have this kind of variable truth value.
Yeah, he seems to have missed that key insight, yeah. But, despite all these early insights by McCall, I think, Lewis is really the one who gets the credit as the father of the syntactic tradition in modal logic.
Right, because he was the one who really kind of systematically built these philosophical worries into a formal system.
Exactly.
With these new intentional connectives.
Yeah, and he was really prolific too in terms of developing these systems.
Yeah.
So starting around 1914, he actually proposed a couple of alternatives to the system presented in Principia Mathematica.
Right.
And he kind of went down a couple of different paths.
Mm-hmm.
So initially he was thinking, well, maybe we can modify the existing system.
Yeah.
And remove those problematic paradoxes of material implication.
Right.
So that it would be sound for both what he called material implication and also this notion of strict implication.
Right.
But more significantly for the development of modal logic.
Yeah.
Was this other path that he took where he constructed a completely new system that was specifically designed to capture this stricter sense of implication.
Okay.
And his 1918 system, presented in a survey of symbolic logic, was kind of an early attempt at this, using impossibility as a fundamental concept.
Right.
But it ran into, a pretty significant snag.
Yeah.
As you mentioned, Post showed that it actually led to this collapse,
right,
where necessity ended up being equivalent to just simple truth.
Right, which is kind of like the opposite of what we want, right?
Exactly. Yeah, it's very philosophically problematic.
Yeah. If
we want to maintain a distinction between what is the case and what must be the case.
Yeah.
So, in 1920, he tried to kind of rectify this with a weaker set of axioms.
Okay.
And then in 1932, in the Appendix to Symbolic Logic, which he co-authored with C.H. Langford, he presented a more refined approach. And this is where he introduced the 5 systems.
Right, S1 through S5.
S1 through S5.
Yeah.
That we now know and love, or at least know.
Right.
And so in these systems, possibility, diamond becomes the primitive operator.
Okay.
And then strict implication, P right ROQ, is defined in terms of possibility.
So it's like neg, diamond, P wedge, neg.
Exactly.
It's not possible for T wedge or Q to be false.
That's right.
Yeah.
So the system S1 was defined by a set of axioms, B1 through B7.
Okay.
And then a set of rules of inference.
Yeah.
And these rules included things like uniform substitution of strict equivalence, adjunction, strict inference.
Right.
And interestingly, later on, McKinsey showed that one of these axioms, B5, was actually redundant.
Oh.
It could be derived from the others.
Okay.
And so then S2 was created by adding a really crucial axiom to S1.
Okay.
It was called the consistency postulate.
Okay.
Which is B8, diamond P and right arrow diamond P.
Right. So that's essentially saying that, like, if it's possible for both P and Q to be true, then it must be possible for be true on its own.
Exactly. Yeah. And then S3 arises by adding yet another axiom to S1.
Okay.
Axiom A8. Mm-hmm. P right arrow, neg diamond, Q right arrow, neg diamond P.
Okay.
Now, Lewis initially favored S3.
Yeah.
Perhaps because it captured kind of a more subtle or nuanced form of necessity and possibility.
Yeah.
But he actually later developed some doubts about it.
Oh, why is that?
Because Weisberg and Perry were able to derive this seemingly problematic theorem in an earlier formulation of S3.
Okay.
Which was P right arrow Q right arrow P right arrow.
Right. So essentially saying that strict implication is transitive.
Exactly. Yeah. And Lewis wasn't entirely convinced that this stronger form of transitivity should necessarily hold for a philosophically sound notion of implication.
Right. Right.
But the funny thing is that later on Perry actually proved that neither axiom A8 itself nor that transitivity theorem were actually derivable in the weaker system S2.
Oh, interesting.
Yeah.
Okay.
So Lewis also introduced what he called the existence axiom B9.
Okay.
Which is diamond P right arrow, diamond TVQ.
Yeah. Okay.
And this had the important consequence of preventing strict implication from collapsing into just material implication.
Right. So we're really trying to distinguish these
Keep them separate.
Yeah.
Yeah, and it also implied that there are at least 4 logically distinct kinds of propositions.
Oh, right.
So you have like necessarily true, contingently false, and necessarily false.
Right.
So it's aligning with this intuition that we have about these different grades of truth.
Yeah.
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 So then we get to the well-known systems S4 and S5, which were built upon S1.
Okay.
By adding further axioms.
Yeah.
Proposed by Becker, C10, C12.
Right. So S4 you had C10. Diamond P, right arrow, diamond P. And then for S5, you had C11.
Right.
Neg diamond P, right arrow box, neg diamond P.
Yeah. Or equivalently.
Or you could add C10 and C12.
That's right. Yeah. C10 and C12.
Box P, right arrow, diamond P.
Okay.
So.
And it's interesting that even though, like, S5 became such a central system in a lot of the applications of modal logic.
Yeah.
Lewis himself thought that the weaker systems were actually.
Yeah, he actually favored exploring those weaker systems, those ones closer to our initial intuitions about implication.
Right. Yeah.
So the ones closer to S1.
Right, yeah.
Yeah.
Okay, so but even with this, this new stricter notion of implication, there were still some paradoxes that emerged. Right.
This idea that an impossible proposition implies any proposition, or that a necessary proposition is implied by any proposition.
Yeah.
And Lewis defended this by saying, look from a logical contradiction, like P wedge neg P, know, both P and neg follow.
Right.
So you can derive anything.
Right.
But this remained controversial.
Yeah.
Especially that principle.
Yeah, that one really read people the wrong way.
Yeah, it just didn't seem to really capture this notion of a genuine, like,
inferential connection.
Yeah, like you can really infer something from that.
Right.
And so this actually led some people to develop, even stricter implication systems like entailment logic. Where they were really trying to find this more, relevant connection between the antecedent and the consequence. Okay. And I think it's important to point out, especially for, folks thinking about this from a philosophical perspective, that the fact that Lewis was trying to formalize all of these, both proof theoretic and semantic notions within the object language, that's what led, Quine to just reject the whole thing.
To reject modal systems altogether.
Yeah. Because he saw that as like an illicit blurring of the distinction between like using a symbol
Right.
and mentioning a symbol.
Yeah, he saw it as this use-mention confusion.
Right.
That was really problematic.
Because after all, if pray arrow q is a theorem in regular propositional logic, then pray arrow q can be proven in S1 and all the stronger Lewis systems.
That's right, yeah.
Right.
So it's really this move of putting all of this into the object language that Quine really took issue with.
Yeah. Okay, so that kind of lays the groundwork for this syntactic development.
Yeah.
But where did things go from there?
Well, I think the next significant development was the introduction of this method called the matrix method.
Okay.
By Jan Jukasevich in the early 1920s.
Okay.
And this represented a kind of a shift towards a more algebraic way of thinking about logic.
Okay.
Where the focus was on evaluating logical systems using, sets of truth values beyond just the traditional true and false.
Okay, so this is more than just like truth tables.
Right. Yeah.
Yeah, we're expanding.
We're going beyond truth tables. Yeah. So Jukasevich initially used this approach to analyze, standard two-valued propositional logic.
Right.
But then he famously extended it to three-valued matrices.
Okay.
In his work on propositions about future contingent events.
Okay, so that's interesting because, as we mentioned earlier, like this very technique would later show that you can't really
modal logic in a three-valued system.
Yeah.
So it's kind of ironic that he was using it for that.
Right.
But what is what's the core idea of a matrix in this context?
So a matrix in the context of both propositional and modal logic involves defining a set of truth values, identifying a subset of these as designated, which represent truth, and then specifying how the logical connectives operate on these values. So for modal logic, you just need to add a unary operation corresponding to the possibility operator, diamond. And these logical matrices became a really valuable tool for showing things like the independence of axioms.
Or the consistency of a given system.
Right. Yeah, so for example, if you can construct a matrix where all the axioms of a system, except for one, evaluate to a designated value, while that one axiom doesn't...
You've effectively proven that axiom cannot be derived from the others.
Right.
And therefore, it's independent.
Okay, so you can really use this to probe the structure of these systems.
Exactly, yeah. And a couple of logicians, Rosser and Meredith, use this method to make some important contributions to understanding the independence of Lewis's axioms.
Okay.
And then Perry, using the matrix method, was able to prove this really interesting result concerning the number of distinct modalities. In Lewis's systems S3 and S4.
Okay.
He was actually able to show that they're finite.
Okay, but before we jump into that, can you remind us what we mean when we say modality?
Sure.
In this context?
So in this algebraic context, a modality refers to a sequence of modal operators, so box and diamond and negations, applied to a single propositional variable.
Okay.
So the degree of a modality is simply the number of modal operators in that sequence. So Perry identified four fundamental forms of what he called proper modalities. Which are those with a degree greater than 0.
Okay.
And he showed that in S3, there are exactly 42 distinct modalities.
Wow.
In S4, there are 14.
Okay.
While the much stronger system, S5, collapses to just 6.
Oh, wow.
Yeah.
That's surprising.
Yeah, and he even investigated these intermediate systems like S4.5.
Okay.
And showed it has 12 distinct modalities.
Okay, so the number of possible modalities, it's not necessarily an indication of how strong or complex
not necessarily
the system is.
Yeah, so he actually found systems that had the same number of modalities, but differed in their logical properties.
Right.
And it's also fascinating that systems like S1, S2, phase system T, and Brouwer system B, all turn out to have an infinite number of distinct modalities.
Wow.
Yeah.
Okay, so now a key concept related to this matrix method is that of a characteristic matrix.
Yes.
Which is, a finite matrix that perfectly captures all the theorems of a given logical system.
That's right, yeah.
And so the interesting thing here is that if a logic has a finite characteristic matrix, It means that the logic is decidable, which means that there's an algorithmic procedure to determine whether any given formula is a theorem.
Right.
But Henkin and Fays proved that none of Lewis's systems, S1 through S5, have a finite characteristic matrix.
That's right.
So they can't be, fully characterized by any finite valued logic.
Yeah, and later Scroggs actually showed that proper extensions of S5 actually do have finite characteristic matrices.
Oh, okay. So there's a kind of an interesting cutoff point there.
Yeah.
But despite this general limitation, McKinsey was able to prove the decidability of S2 and S4. And he did this using these modal matrices with specific conditions that mirrored Lewis's inference rules.
Right.
And he introduced this idea of a normal matrix.
Right.
And his proof involved this clever construction where he basically built a characteristic matrix from the formulas of the system itself.
Right, the Lindenbaum algebra.
Yeah, and then he showed that any formula that wasn't a theorem could be shown to be false in a finite normal matrix.
Right.
So it's a really nice way to kind of bridge this gap between like the potential infinity of formulas and finite, mathematical structures.
Yeah.
So from this point on, this algebraic perspective really continued to evolve, and it became like more abstract. The focus shifted from the specifics of individual matrices to this more general concept of algebras. Which you can think of as like matrices without designated values.
Right, yeah. So for example, Boolean algebras provide this kind of algebraic framework for standard propositional logic.
Right.
And Alfred Tarski was really a big proponent of this generalization.
Yeah.
And he advocated for studying, whole classes of algebras as a way of understanding logical systems.
Okay.
So this led to, some really groundbreaking work by Bjorny Johnson and Alfred Tarski, where they introduced these things called Boolean algebras with operators.
Right.
And these are essentially Boolean algebras that are expanded with these additional operations that correspond to modal connectives.
So like Boxen.
Exactly. And their general representation theorem was a purely algebraic result, which showed how these abstract algebras could be represented as concrete set algebras.
Okay.
So algebras where the elements are sets and the operations are set theoretic.
Okay.
Now, remarkably, this algebraic result actually foreshadowed Kripke's later semantic completeness theorems for modal logic.
Wow.
Although this connection wasn't immediately recognized by any of the individuals involved at the time.
It's amazing how these things kind of come together.
Yeah.
But then, E.J. Lemon, seemingly working independently, also adapted McKinsey's algebraic techniques to obtain decidability and representation theorems for various modal systems.
Yeah, including Fays's system T.
Right.
And he even developed a specific technique for constructing finite algebras based on subsets of what we would later understand as Kripke model structures.
Wow, okay.
So it was really Dana Scott who ultimately provided a general representation theorem that explicitly linked modal algebras to power sets of Kripke structures.
Okay, so he really made that connection.
Yeah, he really brought it.
Yeah.
Expert.